So I picked these out because they pretty much cover the topics that we've covered in the class. Representative, and you already know that my review documents have a lot of overlap in them and a lot of repetition. So in the interest of time, I just picked these out. Okay, so is this working? This is not working anymore. I have to turn it on first. There we go. Okay. I don't need it right now. Gases generally have, and this is number one, gases generally have what properties? Well, they definitely have low density, right? So A would be good, B would not. How about closely packed particles? No, not that one either. No increase in volume when temperature is increased. Charles will take issue with that. No decrease in volume when pressure is increased. Boyle would take issue with that one. So the only one good one for that one is A. They have low density. And if you look at the definition of density, that means that the mass is very small and the volume is very large by comparison. That makes low density. How about two? Pressure is defined as what? Well, basically pressure is force per unit area. But does that answer the question? It's not the mass that the object exerts. It's not measured in newtons because newtons is force, right? So it'd be that one. Number of moles of substance? I don't think so. Defined as the force per unit area. There you go. D. Yep. The SI unit for pressure. We didn't spend a lot of time on this one. But do you remember the unit for pressure in the SI system? It's named after somebody, of course. It's called the Pascal. In the Pascal, 1 Pascal is equal to 1 Newton per square meter. Force per unit area is 1 Pascal. A glass column is filled with mercury. Number 5. A glass column is filled with mercury and inverted in a pool of mercury. So that sounds like Torricelli's barometer. So you got a pool of mercury, and then you got this inverted column in it. And then what else does it tell us? Stabilizes at 729 millimeters above the pool. So from here to here is 729 millimeters. Yeah. There's the top of your meniscus on the mercury. What's the pressure of the atmosphere? And what units? The units are in atmospheres. This is in millimeters of mercury. So you got a unit conversion problem here. Okay. So we're going to take this and make atmospheres out of it. So how many millimeters of mercury per atmosphere? Remember? 760. So you divide 760 into that, and it's a little bit less than 1. And as it turns out, it's 0.959 atmospheres. That's because this cancels that and leaves you with atmospheres. Okay. All righty. Let's see. The next one I got highlighted. 6. The local weather forecast reports that a current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmospheres? Okay, we need a conversion factor. Inches of mercury. If you don't remember that, that's okay. In the back of the document, the review document, there's useful information and there's a list of conversion factors for those things. And if you look it up, you'll find that the conversion is 29.92 inches per atmosphere. So if you divide that into that, it's a little more than 1. And as it turns out, it's 1.02. Okay. The air pressure in the inner tube of a tire on a typical racing bike is 112 psi. That's a lot of pressure. 8. 112 psi. What does psi stand for? Pounds per square inch, right? And it wants to know what is that in atmospheres. All right, so we got another unit conversion. So how many psi is 1 atmosphere? Do you remember? 14.69. You divide that into 112, and you should come up with 7.62 atmospheres. I never had a bike with that high pressure in it. So mine was about 65 psi. Now, I'm not even sure if racing bikes have pneumatic tires anymore. They might have solid tires. I know their rims are made out of carbon fiber, and their bikes are made out of carbon fiber. So who knows? Boyle's law states, right? Remember Boyle's law? Pressure times volume equals a constant. So we just have to find which one of these matches that. The volume of a fixed amount of gas is inversely proportional to the pressure at constant temperature. Whenever you see 2 variables that are product of each other equal to a constant, that is inverse proportion. If that one goes up, this one's got to go down in order to keep that constant. Avogadro's law. Remember what Avogadro's law says? See, I think it's volume and moles is a constant. So if the number of, and remember, the 4 factors that have to be accounted for when we're talking about a gas: pressure, temperature, volume, and moles. So if you're relating these two and letting them vary here, that means these two have to be constant. Temperature and pressure have to be constant in order for Avogadro's law to work. And equal amounts of gas occupy the same volume at constant temperature and pressure. All right, that's another way of saying it. This is actually Avogadro's law, but another way of expressing it is, right, if you have this volume equals that volume, this pressure equals this pressure, this temperature equals this temperature, then it has to have the same number of moles in each container. That's another way of expressing Avogadro's law. All right. Charles' law. Okay, so Charles related volume and temperature, correct? So the volume of a fixed amount of gas is directly proportional to the temperature at constant pressure. That means when you have a quotient of two variables equal to a constant, they're always directly proportional. That one goes up, that one has to go up. All right, let's get out of these easy ones and actually solve some problems. 15. A gaseous chlorine is held in two separate containers at identical temperature and pressure. Two separate containers. We don't know what the volume is on these containers yet, but they both have chlorine in them. Their temperatures are identical, and their pressures are identical. Okay. The volume of container 1 is 1.30 liters. 1.3 liters and contains 6.7 moles. Volume of container 2 is 2.33 liters. How many moles does it have? Okay, this is a before and after problem, as opposed to a state problem. So you could look at it two different ways. Well, actually, volume in moles. Yeah, that's Avogadro's law. So volume 1 over moles 1 equals volume 2 over moles 2. Here's volume 1. Here's moles 1. Here's volume 2. And there's your unknown. So just solve for the unknown. And bring this one over here, take that one over there, and take this one over here, and solve. And we should get 12 moles. Now, is that reasonable? The volume went up, the moles went up. By how much? Well, not quite twice as much. Not quite twice as much. That's reasonable. Okay. 15, 18. Body temperature is about 309 K. K. Is that reasonable? What's normal body temperature in Celsius? Did I tell you that before? 37. Plus 273. So that'd be 10. 13. Okay, it's close. I'll accept that. So that's body temperature, they're saying. On a cold day, what volume of air at 276 K? So this is inside the body, and this is outside the body. 276. Okay. Your lung capacity is 2.20 liters. Your lung capacity is going to be at that temperature. Volume inside the body is 2.20 liters. It wants to know what volume of air at that temperature has to be drawn in, and as it's drawn in, it's heated to this temperature and occupies that volume. So how much does it have to bring in? That's Charles' law, right? Well, let's be consistent. That's B, that's B, B, O, and T, O. So the temperatures are already in K. That's good. We don't have to change them. So the volume in the body is 2.20 liters, and the temperature in the body is 309. Okay. The temperature of the air is 276 K, and this is your unknown. So just divide that one by that one and multiply it by this one. And that should give you 1.97 liters. That's reasonable. It occupies less volume at this temperature. When you bring it in the body, it expands to that volume. I didn't ask anybody if you had problems that we need to get to first. Okay, we'll keep going then. Okay, you're holding two balloons, an orange and a blue. This is 20. Now we got an orange and a blue. I don't know if that's the right volume yet. The orange balloon is filled with neon, and the blue balloon is filled with argon. The orange balloon has twice the volume of the blue balloon. All right. So this one is twice as big as this one. Let me shrink it a little bit. So the volume of the neon balloon is equal to twice the volume of the argon balloon. All right, which of the following best represents the mass ratio? So what we want is the mass of the orange and the mass of the blue. That's the ratio we're looking for. Okay. I think in the worked problems, I go into some algebraic gyrations, but I think maybe just a verbal explanation would probably work best here. If you've got these two different volumes, and we have to assume that they're at the same temperature and same pressure. Otherwise, we can't work the problem. So the temperature of the orange is equal to the temperature of the blue, and the volume, excuse me, not volume, pressure. The pressure of the orange is equal to the pressure of the blue. These are balloons. Okay, so that's reasonable. All right. So how many particles do you have in this one versus that one? You have twice as many over here, don't you? Okay, so the moles of the neon is equal to twice the moles of the argon. All right, if we want to know anything about their mass, we need molar mass to compare them. All right, so argon is about 40. And neon is about 20. Okay, so if you've got twice as many neon particles, but they weigh half as much as the argon, what's their mass ratio? 1 to 1, right? 1 to 1. If we had the same volume, then their mass ratio would be, let's see, this would be 1 and that'd be 2, 1 to 2, because we had the same number of particles. But we've changed two factors at the same time, the number of particles and the mass of each particle. That was 20. Let's see. I skipped a few. Here we go. 29. Gas sample is heated from -20 to 57 degrees and the volume is increased from 2 liters to 4.5 liters. If the initial pressure is 0.14 atmospheres, what's the final pressure? All right, we've got a before and after here, but we've got more than 2 variables changing. So that tells me we need the combined gas law. So we got pressure 1, volume 1 over moles 1, temperature 1 equals pressure 2, volume 2, moles 2, temperature 2. All right, can we get rid of any of those factors so they're not in the way? The moles didn't change, right? That gas was confined and we just let these other variables move. So we can get rid of this one. And now we have P1 V1 over T1 equals P2 V2 over T2. Now we have to decide which is which. P1 V1 T1 P2 V2 T2. So what's the initial pressure? The initial pressure is 0.14 atmospheres. 0.140 atmospheres. And this pressure is the one we want to know. The initial volume, it goes from 2 liters to 4.5 liters. So we've got 2 liters here, 4.5 liters there. And the temperature changed. -20 up to 57 degrees C. We're going to have to change this one and that one to Kelvin. Plus 273, plus 273. So this one equals 253K. And this one equals 10, 1 and 12 is 13, 330K. There we go. Now that we've got everything where it needs to be, we can use the formula. And we just plug these in. That one goes there. This one goes here. That one goes there. And this one is unknown. And V2 goes there. And T2 goes there. We solve for that unknown. Okay. And if we do our math right, we should come up with 0.0811 atmospheres is equal to P2. Okay. All right, 30. Sample of oxygen has a volume of 1.72 liters. Sample of oxygen has a volume of 1.72 liters. At what temperature? 27 degrees and 800 torr. Pressure is 800 torr. How many oxygen molecules does it contain? So is this a before and after or a state? Try state. We don't know what it was before. This is where we are right now. And they want to know how many oxygen molecules They actually want to know not just the moles, but the number of molecules. But what formula gives us this answer? Ideal gas equation, right? So this needs to be converted. The units of measure here for R liter atmospheres per mole K. That tells you the units of measure for each of the factors. This one needs to be in atmospheres. Okay, divide by 760. This one needs to be in Kelvin, plus 273. That one's good, it's liters. And moles, it'll come out, the answer will come out as moles, and then we have to convert it to the number of molecules. So let's solve this one for moles. That's PV over RT. And then pressure is going to be 800 divided by 760. 1.053 atmospheres. Volume is 1.72 liters. R is this one. All right, I'm going to leave the units out for now. And the temperature is 300. Okay. So all we have to do, this is the intermediate step, times 1.72 divided by 0.08206 and divided by 300 is 7.35 times 10 to the minus 2 moles. Right. And the question was, how many oxygen molecules? So we got to convert moles to molecules. Moles on the bottom, molecules on the top. So what's the magic number here? Avogadro. 6.022 times 10 to the 23rd times that value. Yeah, let's see, how many significant figures? Yeah, probably 3. 4.4, yeah, 4.43 rounded off. Times 10 to the 22nd molecules. Okay. Let's see, who's next? You know, time. Okay, we're okay. All right, this is memory work. 37. Under what conditions of pressure, temperature, and moles is the gas behaving most ideally? Remember? Low pressure, high temperature, and low moles. That will give you an ideal gas behavior. And when do you get those conditions? Well, like right now, breathing air in and out. The air in the room meets those conditions. Low pressure, 1 atmosphere is low pressure. 200 and, I don't know what the temperature is in here. 293, 295, something like that. K is high temperature and low moles. Number 40. 41.1 gram sample of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure of the same conditions of volume and temperature? Okay, so if we've got a sample of neon, that's 41.1 grams. Okay. Fixed volume and pressure. So we want what mass of argon? Mass of argon will give you the same, give you half the pressure. So the pressure of this one is equal to 1/2 the pressure of neon under those same conditions. And we want to know what mass will do that. Okay. So if this is going to be exerting half the pressure of that one, it needs to have half the number of particles, doesn't it? So the moles of this one have to be half of the moles. Oops. Half the moles of this one. And if this one's got half the moles, then how do we relate masses? Well, we did this before. This is about 40. This is about 20. So if this has got, if this is going to exert half the pressure, it needs to be half the number of particles, which means that if you have, say, let's just say we have, well, we do have 41.1 grams, 41.1 grams. So we can convert that. In fact, we can use the exact value for neon, which is 20.2. 20.2 grams. So how many moles is that? .035. 2.035 moles of neon. And the pressure is related to moles. So if the pressure goes up, the moles goes up, the pressure goes down, the moles goes down. So in order to get half the pressure over here, we need half the number of moles, right? So divide that by 2, 1.017. 1.017 moles of argon. So we can convert that to mass of argon. So let's get an exact value this time. Argon is 3995 times 1.017. Messed up. 1.017 and 39.95. 40.6. 40.6 grams. Close. The best answer would be E. Okay. I thought I was going to be able at the beginning to reason that out, but it turns out we needed an exact calculation. Let's see, next one on the agenda. What's that? 4 identical. Oh, okay, so this one stands alone, 49. So of these gases, which molecules are diatomic? Oh, that's too easy. Which one's diatomic? there. 52. The mass of 1.12 liters of gas Y. So we have a gas Y, 1.12 liters volume, and the mass is equal to 6.23 grams. 6.23 grams. Oh, what's the density? Mass divided by volume. Let's check our units. Right now they're in grams and liters. Is the answer in grams per liter? Grams per liter. Yeah, grams per liter. So we can just take those values, divide this one by that one, and it should come out in the neighborhood of 6 or 5, between 5 and 6. B. Okay. Just shove the numbers in there. How about 53? Oh, it's the same gas. Okay, I probably shouldn't have erased that information. So we got the same gas. The molar mass of the gas. All right, 1.12 liters of gas. Any other information given? No. 1.12 liters. Fine. And mass is 6.23 grams. Okay. The question is, what's the molar mass? But what do we need to know for the molar mass? We need to know mass per unit mole. We got the mass. How do we get the moles out of 1.12 liters? Standard temperature and pressure. What's the standard temperature? 0 plus 273. Pressure, 1 atmosphere. Okay, so we've got volume, temperature, pressure. Yeah, we can find the number of moles. PV equals nRT. Number of moles equals PV over RT. So pressure is 1 atmosphere. Volume is 1.12 liters. R is 0.08206. And temperature is 273. So that would give us the number of moles. 0.08206 and 273. 4.999 times 10 to the minus 2. Moles. Okay, so we got mass, 6.23 grams for how many moles? And that's equal to 125 grams per mole. C. Okay. Let me see here. Argon has a density of 1.78 grams per liter at standard temperature and pressure. How many of the following gases have a density at STP greater than that of argon? All right. Let's see. Argon, and the density is given as 1.78 grams per liter. 1.78 grams per liter at standard temperature and pressure. And our other gases are chlorine, helium, ammonia, and nitrogen dioxide. So we want to know how many have a density greater than argon. So we're looking for a density that's greater than argon. The if we're looking at, if we standardize things at 1 mole, like 1 mole of gas, then at standard temperature and pressure, they should all have the same volume. So the volume is going to be fixed. What we want to know is in that volume, and they have exactly the same number of particles, right, according to Avogadro. So if they have exactly the same number of particles in that fixed volume, then all we have to do is compare their molar masses. So this one's about 40. This one's 3545, which is 70.9. Helium is 4. Ammonia is 14 plus 3 is it's about 17, a little more than 17. 14 plus 32 is 46. Okay, so which one should be more dense? The heavier one. The heavier ones. Right? So this one and this one. Those two. So there should be 2 of them that are heavier, denser than argon. Did that reasoning register? Okay. Let's see. Which of the following is the best qualitative graph of pressure versus molar mass? 1 gram sample of different gases at constant volume and temperature. Okay. We want a pressure versus molar mass. What are we? E. Oh, that's the answer. What's the number? 56. So we want to graph molar mass versus pressure for gases, and they're all the same mass. Let's see. Yeah, they're all the same mass, constant volume and temperature. Volume and temperature. So if we have 1 gram sample, of the different gases. So what happens as the molecular weight of the gas increases? What we're trying to relate here is the number of particles, right? As the number of particles goes up, the pressure should go up. So if the molecular weight increases, what is that doing for the number of particles in a 1 gram sample? It goes down, right? As the molecular weight goes up, the number of particles goes down. So as the molecular weight goes up, the pressure should come down. So we're looking at something like this. Pressure times molar mass is a constant. So we should get a hyperbola, which looks like Boyle's law. And none of them match. That's why the answer is E. Did that register? Okay. Sometimes I wonder if I'm explaining it right. Makes perfect sense to me. That's not our goal. Our goal is for it to make sense to you. Okay, 58. This one, I could work 58 two different ways. And I have done it two different ways. One is sort of algebraic, where we just say, let X equal something. The other way is to use these concrete numbers and calculate to give you the ratio of pressures in the container before and after the reaction. That's what they're asking here. And I think usually students that are new to chemistry, unless they're really good and feel comfortable with algebra, that the concrete method works better. Now the worked problem, if you look at 58 worked problem, it's going to give you an algebraic explanation. So that's why I want to do this one concrete. So we have this reaction, ammonia plus chlorine to ammonia plus 3 chlorine, I think. Yes, yields nitrogen plus 6 HCl. Nitrogen plus 6 HCl. And these are all gases. Okay. We're also given 5 liters of ammonia and 5 liters of chlorine. All right. Notice that, let's see, is this balanced? 6 hydrogens? Yep. 2 nitrogens? Yep. 6 chlorines? Yep. Okay, we're balanced. Next thing you notice is that we're given absolute amounts of reactants, which should be screaming at you, limiting versus excess. So one of these is going to run out. We need to find out which one runs out. And what it's asking for is the ratio of pressure final versus pressure initial. Pressure final, pressure initial. This ratio, all other factors being equal, which same conditions, yes, all factors being equal, this ratio is also final moles, initial moles. All right, so we can do something with that, with moles. Okay, so in order to do this in a concrete way, since the conditions are the same before and after, we get to pick the conditions. And probably the easiest way to do it is standard temperature and pressure. So if we have 5 liters of ammonia, how many moles is that? Let's go ahead and do it here. PV equals nRT. So the number of moles is going to be PV over RT. And we pick the conditions. Pressure is 1 atmosphere. Volume is 5 liters. And R, 0.08206. And temperature is 273. 0 degrees Celsius. Right. If we do that, then we've got the same number of moles here as we do there. Exactly the same. So we only need to do one calculation. So the number of moles of ammonia is the same as the number of moles of chlorine, which is 5 divided by 0.08206 divided by 273 is, let's see, the standard notation, this is 0.2232 moles. Let's see if I did that right. 5 divided by 0.08206, 273 So we've got this many moles of that one and this many moles of that one. Now, how do we find out which one's limiting? We take this many moles of that one and convert it all to one of those. I'd say nitrogen would probably be the best, because once you know how many moles of nitrogen are produced, 6 times that is how much this is produced. So I would go with this one. So if we say this is ammonia, and nitrogen, what's the ratio? Well, 2 here and 1 there. So if we use all of that, it'll produce 0.111116 moles of nitrogen. But if we have chlorine, and we convert chlorine to nitrogen, that's 3 to 1. .0744. 0.07. 0.0744 moles of nitrogen. This is limiting. Chlorine is limiting. Okay? So the final number of moles is this much nitrogen times 6 equals 0.4464. 4464 moles of hydrogen chloride. Okay? So the final number of moles here is, add those two together. .5208. Zero. Ooh. What mistake did I just make? We didn't use all this up, did we? So this is part of the answer, that one plus that one. But I need to know how much of this is left over. All of this is gone. It's over there now. But this one was 0.2232. Let's do it this way. Yeah, we can do it. We can do it. Okay. We started off with chlorine at 0.2232 moles of chlorine. We want to find out how much of ammonia was used. All right, so chlorine's here and ammonia's here. And the ratio is 3 chlorines to 2 ammonias. We did one. No, we did a third. So 0.2232 times 2 divided by 3 is 0.1488. Moles of ammonia consumed. How much is left over? 0.2232 minus 0.1488 equals what? .0744. 0.0744 moles ammonia remain. Okay, so this one left over, and these two have been produced, this one and this one. So we add those three together. Well, actually, I can take 2 times that value. And then 0.4464. And that's 0.5952. 0.5952 moles. Our product, what was the initial? How many moles initially? 2 times this, right? 1 for the ammonia, 1 for the chlorine. .4464. 0.4464 moles. Okay, so let's divide that one into 5952. It's still in my calculator. I get 1.33. So this ratio is 1.33 to 1. Okay. I know that was a lot of. Actually, it takes longer to do it this way than it does the algebraic way. But you get the same answer, which is C. The trick to this one is recognizing that the ratio of the pressure is the same as the ratio of the moles. All right. We're doing on time. Okay, we're still good. 61. When 0.72 grams of a liquid is vaporized at 110 degrees and 0.967 atmospheres, the gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Okay. If the empirical formula is CH2, what are we looking for? That multiplier. And how do we get the multiplier? We know the empirical mass because we can calculate it. CH2, 1 carbon and 2 hydrogens. What we need is the true molar mass. And then we ratio the molar mass to the empirical mass and get X. And then we're home. So what we have to do is find out what is the actual molar mass of the gas. So in order to do that, we need mass and moles. So we have mass, yes, 0.72 grams. What we need is moles. So do we have the information we need? 110 degrees Celsius is the temperature, pressure, volume, probably give that too. 0.967 atmospheres. How about volume? 0.559 liters. Yep, we just have to convert this one to Kelvin. 383, right? Yeah. Okay, and now we can find moles. PV over RT, right? Pressure, atmospheres, volume, R, and T, 383. I would do fancy calculator work here. 0.559, 0.08206, and 383. So I get 1.72 times 10 to the minus 2. 1.72 times 10 minus 2 moles. And that will give us the molar mass, the true molar mass of the gas, the material that was vaporized. 41.86 grams per mole. Okay, so what's the empirical weight? That's the molar, that's the true molar mass. The empirical weight is 12.01 plus 2.02 for 2 hydrogens. So the ratio then would be this. $41.86, yeah, and then 14.03. That's approximately 3. Closest whole number is 3. So that's our multiplier. This equals 3. That means we have C3H6. C. Okay? Alrighty. Keep moving along here. Eventually we'll get to the end. Must be a lot of repetition in there because I skipped a bunch, didn't I? 80. Okay. If M is the molar mass, R is the gas constant, T is the temperature, okay, P is the pressure. Which of the following expressions represents the density of the gas? So we're looking for density. Density equals what? Well, density needs to be mass per unit volume. Right? Was volume given? Volume wasn't given. What else do we know? Well, we know molar mass equals mass per moles. And since it's a gas, the ideal gas equation is probably in there somewhere. PV equals nRT. So we got this one. We've got this one. And we've got this one. So we want to end up here. So let's look at the relationship here and see if there's anything we can do with this one. What do they have in common? This one right here. Right? So if we solve this one for moles and substitute it in here, what do we get? We get M equals mass over PVRT, or mass times RT over PV. Okay? Now, what do these two have in common? Well, this is equal to that, and they share that variable right there. So we need to solve this one for that mass. Right? That mass is equal to this molar mass times PV over RT, correct? Did I lose anybody? Okay. Now we can substitute this right here. So density equals, let's see, big M PV over RT divided by V. Okay. This is in the numerator, that's in the denominator. This is in the denominator of the numerator, so it's in the denominator. So that's equal to MP over RT. Does anyone fit that? A works. We just have to flip these two. I guess algebra helps in this case. Okay, 81. Let's see if I can, let me move this out of my way. Here we go. One way to isolate metals from their ores is to react the metal oxide with the carbon as shown in the following reaction. Okay. So with this generic reaction, 2 times MO, that's a solid, reacted with carbon, right? Yep, yields 2M solid plus CO2. And what's the identity of the metal? What is that one right there? Well, let's see. What else do they give us? 34.08 grams of this. Okay. React with excess carbon. Okay. And 4.37 liters of CO2. 4.37 liters of CO2 is formed at 100 degrees C and 1.5 atmospheres. So we got to get at that. So how are we going to identify the metal? We don't know the number of protons. We don't know the Z number, right? So we have to go for the molar mass, right? If we can find the molar mass, then we're good. So what we need to know is number of moles of this, number of moles, the mass of this, and the number of moles of that would give it. But all we can do for sure is with this information, volume, temperature, atmospheres, we can find moles of CO2, right? Because we've got these three terms. We can find the number of moles of CO2. So the pressure is 1.50 atmospheres. The volume is 4.37 liters. These are all standard units based on that R. And the temperature, 373, right? That's plus 273. Okay, so we can find the number of moles of CO2. Let's see how that helps us. 1.5, 4.37, 0.08, 206, and 373. 0.2142. Moles of CO2. Okay. Now, we could convert that to moles of this, but we don't know what that mass is yet. We could find out this many moles would be that much mass, but we don't know this either. So I think, why don't we find out how many moles this is? Right? It's 2 to 1. MO. Okay. So this is 1, that's 2. So 2 times that value is the number of moles. 2 times 4283. 0.4283 moles of MO. So we can find out the molar mass of that thing. Is that going to help us? $79.57. 79.57 grams per mole is that one right there, or MO. I think it's going to help us. All right, how do we get that value? If we were calculating that and we knew that this was one metal and this was one oxygen, we would have a total molar mass is equal to whatever the metal molar mass is plus 16 for the oxygen, right? So if let's subtract 16 from that one, 63.57, that would go right here, grams per mole. So what's 63.57? Let's see. The closest one I can find is copper. Okay. It wasn't obvious in the beginning how we were going to get there. I was just working with what we had. This is all we got to go on. So picture came clearer as I was calculating things. Well, it's 81. $82. Oh, what's the standard temperature for gases? 0 degrees. Standard temperature for everything else is 20. No, 25. But the standard temperature for gases is 0. Standard pressure, 1 atmosphere. $86. A 142 milliliter sample of gases collected over water at 22 degrees and 753 torr. What's the volume of the dry gas at STP? Okay. Okay, so the total volume equals 142 milliliters, right? What's the nature of this gas we're collecting? It's a combination. I mean, it's a solution of two gases, right? It's our, whatever our gas is, it's our gas plus water vapor, right? And that's equal to 753 torr. The pressure of this one plus the pressure of that one. Okay. So what's the pressure of the gas? Well, we need to know what this one is, so we can subtract it from that one. And at 22 degrees, it says that's 20 torr. So the pressure of the gas is equal to 753 minus 20, which is 733 torr. Okay, so now we know the pressure of that gas. We know the volume. No, the volume is what we're looking for. Okay. So this difference in pressure between 733 and 753 is a ratio of moles, and if they're at the same pressure and temperature, I mean, if they're at the same temperature, then the fraction of volume that's occupied by the gas, all we have to do is subtract the ratio of total volume. So the mole fraction of this one is 733 divided by 753. 0.9734. So our gas occupies only this portion of that volume, and the rest of it is occupied by water vapor. So if we multiply that times 142, we should get the volume that's occupied by our gas. 138. Which is not up there. It's none of these. Okay. All right. 88. Good. A half hour. Oxygen gas generated by this reaction. 2 potassium chlorate yields 2 potassium chloride plus how many oxygens? 3. All right. Collected over water at 27 degrees. Temperature equals 27 degrees C in a 1.55 liter vessel. Volume is 1.55 liters. And the total pressure of 1 atmosphere. So the total pressure is 1 atmosphere. The vapor pressure of water at 27 degrees is 26 torr. So this is 760 torr. And the vapor pressure is 26 torr. So the pressure of water is 26 torr. Okay. How many moles of KClO3 were consumed in the reaction? So what we need to do is decide how many moles of oxygen are we talking about and convert. Right? So the pressure due to the oxygen is 1 atmosphere minus this much. 733 torr, or millimeters of mercury. So we need atmospheres, right? 734, 760. 0.9658. 0.9568. Did I do that right? No, 9658. My dyslexia is kicking in. There we go, atmospheres. So now we have pressure, volume, temperature. We can find moles. So pressure is 0.9658 atmospheres. Volume is 1.55 liters. R 0.08206. And temperature is 273. So that would be 300 K. So the number of moles of oxygen is that. I get 6.081 times 10 to the minus 2. 6.081 times 10 to the minus 2 moles of oxygen. We want to know, the question was how many moles of KClO3. So we've got our ratio here, 3 to 2. Three here, 2 here. So 2/3 of that is 4054 times 10 minus 2. 54 times 10 minus 2. But the answer is standard notation, isn't it? So 0.0405 moles. C. Okay. All right. 94. So we've been using ideal gas equation for the past couple of problems and Dalton's law of partial pressures. Now we're going to use Boyle's law and Dalton's law for 94. You got these two cylinders of gas. They're connected with a valve. Okay. The one on the left is 3 liters. One on the right is 2 liters. Okay, we know that much. The valve, gas pressure in the 2 liter is 1.8 atmospheres. And the one on the left is 3 liter bulb in which the gas pressure is 3 atmospheres. I'll be sure I get those numbers right. The valve between the 2 liter in which the gas pressure is 1.8. Yeah, okay. So when we open that valve, we want to say, all right, what's the pressure when they equilibrate? There's no direct way to get to that one. What you have to do is to break it apart into 2 separate problems and then add them back together when you get the results. So if we assume that this side is evacuated, there's nothing in there. Then we've got a before pressure and a before volume and an after volume. So we can find out the after pressure due to that one. And then we can do the same thing for this one and say that's a vacuum. What pressure would that contribute? And then Dalton says you can add them back together and get the final pressure. So this one's going to be, well, overall, we've got P1 V1 equals P2 V2. So if we work this one with that as a vacuum, then the P1 is 3, and the V1 is 3. The P2 is unknown. What's the V2? What's the final volume? 5 liters, 3 plus 2. Okay, so P2 for this side is 15 divided by 3, right? Wait a minute, I did something wrong. Pressure, volume, pressure, volume. No, that's right. So 15 divided by 3 is 5, right? That doesn't seem right. No, it can't be right. What's wrong with this picture? Nobody caught me. P1, V1 equals P2, V2. I gave them a direct relationship and they're supposed to be inverse. Let's try that again. Okay. So 3 times 3 here, and then P2 times 5. Now it's 9 divided by 5 is P2. Atmospheres. On this side, we've got 2 times 1.8 equals P2 times 5. So this one is 3.6 divided by 5 equals P2. So we add those two together, right? So 3.6 plus 9 is 12.60. So we add these two together. 12.6 divided by 5. 2.52 atmospheres. Now, is that reasonable? If this one's got 3 atmosphere pressure and that one's got 1 atmosphere pressure, which way is the gas going to move when you open the valve? It's going to go that way until it reaches a pressure less than that and greater than that. So that's reasonable. And it's one of the answers too. If I could just get my formulas right. Okay. Oh, 95 is too easy. The partial pressures of each of these gases, CH4, N2, and O2. So this one is 135 millimeters of mercury. N2 is 508. And O2 is 571. All right. Question is, what's the mole fraction of nitrogen? This one. So the mole, remember that the moles are proportional to the pressure, according to Avogadro. So we can say 508 divided by 508 plus 135 plus 571. That's the mole fraction. And it should be 0.418. Mole fraction of nitrogen. Okay? Let's see, Dalton's law of partial pressures. This should have come earlier. The total pressure of the mixture of gases is the sum of the partial pressures of all the gases. We'll move on. Calculate the root mean square velocity for oxygen molecules in a sample of oxygen gas. So we want the number 103. 103. Root mean square velocity of oxygen gas is square root of 3RT divided by molar mass, right? Does that ring a bell? It's in the back of your useful information if you can't remember it. Okay, so we need R, but this time we need R with energy in it. So we have to use a different R. We also need this molar mass in standard units. Right? So the molar mass of oxygen would be 32 grams per mole. But in order to use SI units in this calculation, this needs to be not grams, but kilograms. So how do you get kilograms out of that? Well, if you take 1,000 times out of that, put it over here, then this has to move smaller, right? Units get bigger, number gets smaller. So we say 32.00 times 10 to the minus 3 kilograms per mole. Now we can put our things in there. Temperature, excuse me. 11.8 degrees C. And that has to be, let's see, 284.8 C. Okay. Okay, so now we can do our calculation. 8.145, 3145. 8.3145. Temperature is 284.8. And this is 32 times 10 to the minus 3 kilograms per mole. Okay. That's the thinking part. The rest is number crunching. Take the square root. So I get 471.2 meters per second. So that would be C. That's how fast those oxygen molecules are moving on average. The root mean square velocity. Now what good is that? Well, we can use that velocity and the mass of a molecule to determine what's the kinetic energy, the average kinetic energy of each molecule, if we want. Alrighty, we're getting close. Which of the following is included as a postulate in the kinetic molecular theory of an ideal gas? Kinetic molecular theory. Okay, the distance between gas molecules is small compared to the size of the molecule. No, the distance is large compared to the size of the molecule. The distance is huge. So it can't be A. All collisions between molecules are elastic. That's true. They don't interact with one another when they smack. In an average collision between molecules, both molecules have the same kinetic energy. No. The total of their kinetic energies when they arrive at one another is the same after as it was before. That's the definition of an elastic collision. Right? So C is false. All molecules move randomly in zigzag directions. Well, if they had stopped it randomly, that would be okay. Molecules do move randomly, but not in zigzag directions. Right? They move straight until they hit something. So D is false. They just went a little bit too far. All the molecules have the same velocity. Nope. There's a root mean square velocity that's sort of a weighted average for all the molecules, but they don't all have the same velocity. They'll have a distribution of velocities. So if you have numbers of molecules on this axis, and the velocities on this one, then they'll go like this. They have a bell-shaped curve. In statistics, we call that a normal distribution. Very common in nature. See that. Graham's law. What does Graham's law say? Well, the rate of effusion, the rate that atoms move or molecules move in a gas, is inversely proportional to their masses, right? Their molar masses. Let me get that out of the way. To their molar masses. But it's not just that, it's inversely proportional to the square root of their molar masses. So that's why E is the answer to that one. That's Graham's law. Okay, we ought to be getting close. 116. Let's see. Only got 12 minutes left. Hydrogen and chlorine gases react to form HCl. Okay, so hydrogen gas reacts with chlorine gas and it yields HCl. Okay, so we need two of these. Oops, that's a 2 there. That's it. It's balanced. You and a friend are on opposite sides of a long hallway. It should say opposite ends of a long hallway. You've got the H2, right? So you've got the H2, and your friend's down here with the Cl2. But you haven't released them yet. You want to form HCl in exactly the middle, right here. Okay. Question is, let's look at our answers. Which of the following are true? Who should release first? Well, which one's going to travel faster? Hydrogen. Hydrogen's going to move faster. So hydrogen should release later. Right? Release chlorine and give it some time to get down here, and then release hydrogen, and it'll race to the middle. So chlorine should be released first. B, your friend should release chlorine first. $117. Order the following in increasing rate of effusion. Increasing rate, so they move faster. F2, Cl2NO, Cl2NO, NO2. Yep, and CH4. So what's the factor that controls the rate of their effusion? Molar mass. So this one's going to be about 38, right? 19 each. This one's going to be 35, 45 would be 70, 70.9. This is going to be 14 plus 16, 30. This one's going to be 14 plus 32, which should be 46. And this one's going to be 12 plus 4, about 16. I don't have to be exact to put them in order. So which one's going to move in increasing rate? So what's the slowest one? That one. Then the next one, this one. Right, that one, that one. What's left? This one. And then the next fastest one is this one. And the fastest one is this one. Okay. So is that NO2, F2, NO? Yep, that's A. Uh, 118. Am I getting close? I got a few more. Because 118, because real gas particles have attraction for one another. 118. Real gases act most ideally at STP. Well, that could be. Let's see if there's a better one. We assume gas particles have negligible volume. All right, here's the key to this one. Because real gas particles have attraction for one another, because they have attraction, then the result is one of these choices. Because they have attraction has nothing to do with real gases act most ideally. Or B, we assume gas particles have negligible volume. That's nothing to do with attraction. 1 mole of an ideal gas has 22.4 liter volume. No. Real gases act more ideally at higher temperatures and lower pressures. Yes, that's the best answer. D. That's kind of a tricky one, actually. I mean, if you overthink it, then you could get in trouble. Of all the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? In other words, which ones are less likely to attract their neighbors? So we've got this one. Let's see, what is it? 124. We've got hydrogen gas, chlorine, ammonia, and oxygen. Okay, which ones are least likely to attract one another? Well, first, look for any polar molecules. Right? Which one's polar? That one right there. Looks like this. Right, so it's polar like that. Right, so we can throw that one out. How about the others? Well, the others are nonpolar. Right? So in order to minimize attraction, you need something that's going to move really fast, and if they're all at the same temperature, move really fast and have very low mass, and that's hydrogen. The one that would be next most attracted to one another would be this one. That's the next biggest one. And then oxygen, and hydrogen would be the least. Whoops. Okay, this one can be a little tricky. Because on the surface, it's not real clear how it's constructed. That's why I draw a picture with this one. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. So this is a sample of gas, 2.34 liters. And it's attached to a manometer. So a manometer measures the pressure inside that container. And the way it's going to look is like this. But it's open to the atmosphere because it says the mercury level, atmospheric pressure, the arm, right, 24.3 torr lower here than the arm that's open to the atmosphere. That's the difference here between these two. So if this is open to the atmosphere, we need to know what the atmospheric pressure is. 1.23 atmospheres. Okay, so the question is, what's the pressure of the sample gas? Well, look at the answers. The answers are in torr. So we need to convert this 1.23 into torr. Right? 760 times 1.23. 853. 853 torr is bearing down on this. But there's enough pressure inside this vessel to not just match that pressure, but to exceed it by 24.3 torr. Right? It pushes this side down further. $877 torr. Now, why is that not working? Did I do a calculation error? 1.23760. Yeah, I did. 934. Plus 24. 959. There it is. E. Okay. So this one, it really helps to draw a picture to get an idea of what they're asking here. Now, do I have any more?